Hi everybody, welcome back to the Feynman technique. Today we're going to be evaluating this integral right here, and let's just go ahead and jump right in. First thing we're going to do is perform a familiar step. We're going to break this up into two separate integrals. The first one going from 0 to 1. And of course the second one going from 1 to infinity. Bringing the second expression to 1 over x will give us this. That's just going to give us the integral from 0 to 1 of natural log squared arctangent 1 over x squared plus 1 dx. You can work out the details of that for yourself. It is true. Okay, well, that's great. But what are we going to do about this arctangent 1 over x? Well, about a month ago, I derived a cool trig identity. And I'm going to rederive it right now. I hope you guys would all agree with this, that the integral from 1 to x of 1 over t squared plus 1 dt is equal to the integral from 1 to x of 1 over t squared plus 1 dt. Right, I mean, you can't get much more true than that. All right, we're going to bring the second expression to 1 over x. So that's going to give us, well, I'm actually going to evaluate this. That's going to give us arctangent of x minus arctangent of 1, which is pi over 4. And that's going to be equal to the integral from 1 to 1 over x of, let's see, it's going to be negative 1 over t squared plus 1 dt, right? I just made a substitution on the second part where x is going to 1 over x, and you end up with this expression right here. All right, so now let's go further with it. That means that arctangent of x minus pi over 4 is equal to negative arctangent of 1 over x plus pi over 4. All right. So now we have our identity. One second here. Yeah. Okay. Yeah, that's this is basically our identity right here. But what we really want to say is that arctangent of 1 over x is equal to, let's see, bring that to that side, bring this to that side. It's going to be a pi over 2 minus arctangent x. Yeah, that's the identity right there that I wanted to show. So we can replace this arctangent 1 over x with that expression right there. So we'll say this is pi over 2 minus arctangent x dx. All right, so now something really nice happens. Now we can see pretty clearly that I is equal to the integral from 0 to 1 of, well, let's see. In the numerator, we're going to have let's see, natural log squared arctangent x plus pi over 2 natural log squared x minus natural log squared x arctangent x, and then we have the same denominator. This cancels with this, which is awesome, which just makes this equal to pi over 2 times the integral from 0 to 1 of natural log squared x over x squared plus 1 dx. All right, so that's much nicer than this, if you know some tricks. All right, let's get rid of all this. And let's re-parameterize our integral like this. We'll create a function of t that's equal to pi over 2 times the integral from 0 to 1 of, let's get rid of that pi over 2. We'll just say it's equal to the integral from 0 to 1 of x to the t over x squared plus 1 dx. All right. Let's immediately take f double prime of t. That's going to be equal to the integral from 0 to 1 of x to the t natural log squared x over x squared plus 1 dx. And we can say that if we took f double prime, evaluated it at the point 0, and then multiplied it by pi over 2, we would get I. Because if we took f double prime at 0, this becomes the integral from 0 to 1 of natural log squared x over x squared plus 1, and then multiplying it by pi over 2 gets us this thing, which is equal to I. All right, where to go from here? I guess I really need to write this down. This is true, that the sum as n goes from 0 to infinity of negative 1 to the n times x to the 2n is equal to 1 over x squared plus 1. And that's true on the interval 0 to 1. One of the bounds is included, the other isn't, but we can get around that by taking a limit if we had to, so we won't worry about it. The only thing, for our purposes, this is true. So we can rewrite our f of t using this fact. So that means that f of t is equal to the sum as n goes from 0 to infinity of, let's see, x it's the integral from 0 to 1 first. The integral from 0 to 1 of x to the t times the sum as n goes from 0 to infinity of negative 1 to the n times x to the 2n dx. No problems with convergence. We can bring that x to the t inside there as a power on x. So all in all, this is just going to give us the sum from n equals 0 to infinity of negative 1 to the n over 2n plus 1 plus t. All right, so there's f of t. Well, we want f double prime of t for the purposes of evaluating our integral. All right, so f double prime of t is going to be equal to the derivative with respect to t, well, the second derivative with respect to t of this expression right here. And I'll just tell you that's going to be equal to 2 times the sum as n goes from 0 to infinity of negative 1 to the n over 2n plus 1 plus t all cubed. All right. Well, there we go. Now, literally, all we have to do is use this fact right here, that if we take f double prime evaluated at 0, multiply it by pi over 2, we get I. So, finally, we have I being equal to this thing evaluated at the point t is equal to 0, then times pi over 2. So that's just going to be pi times the sum as n goes from 0 to infinity of negative 1 to the n over 2n plus 1 all cubed. And that's it. And this this can actually be brought a bit further. I have not shown what this sum evaluates to, but it does have a nice expression. I'll let you guys research that on your own if you want. I have not shown, like I said, I haven't shown on this channel what this sum evaluates to. So I'm just going to leave it as that sum for now. Maybe in a later video, I'll get into some of these types of sums and how you actually, find nice expressions for them. But for now, this is how I'm going to leave it. I just want to check to make sure that I got it right. Yes, pi times the sum from n equals 0 to infinity, negative 1 to the n over 2n plus 1 all cubed. That is it. Hope you enjoy.